Kowalski, we are grateful to you. You have accepted our request for organizing this workshop, which is basically for the National Accreditation Board of Testing and Calibration Laboratories and legal metrology officers of the states and the Union of India, where we are providing regular training programs or workshops on different topics for the betterment of our participants. Sir, as we requested, today's topic is how to do the calibration and testing process for mass comparators. Actually, now in India, we are using large number of mass comparators, but we are not able or we don't know how to do the calibration as per the international practices. So we requested you, because most of us are are working hard in this field to get these equipments calibrated and tested as per the OIML recommendations or as per the best international practices. Sir, we have with us the participants from different organizations, few of the students who are participating in this program, and we have our legal metrology and the laboratories which are working in this field. So basically this legal metrology in India, we are doing calibration, testing, verification, and other aspects of the legal metrology in the country. We have large number of weighing and measuring instruments available in our country, which are verified on yearly basis. All the weighing and measuring instruments which are required to be verified and stamped every year, they are being done. My request is kindly let us know how you are doing in UK and what are the processes by which we can do this calibration and testing of these non-automatic weighing instruments as per the best international practices. Sir, over to you.
Okay, I thank you for inviting me. I will now try my best. I'm not used to this webinar. We normally use Teams, but I'm going now to try and share my screen.
Please, sir. Sir, I would like to introduce Professor Tony Kolsky. He has studied applied chemistry at the College of Science and Technology in England and earned his diploma in chemistry. He was employed by a bulk chemical manufacturer, initially in quality control, then in product development, learning GLC, HPLC, AAS, and culture counter instrumental techniques. Following from this and with experience gained, moved to a research post at the University of Newcastle. He joined Sartorius 1984. Oh my God, you have very large, very big experience. 1984. Now it is more than 40 years and held several positions including technical manager, senior product manager, channel manager, and is currently manager of metrology for premium mass comparison solutions and is actively involved in both sales and product developments. Sir, I'm really thankful to you. You have accepted our request. We are obliged. Kindly enlighten our participants with your knowledge, with your experience, so that we can also follow or comply the best international practices. Sir, over to you, please.
Okay, can you give me permission, please, to share my screen?
Santoshji, can we allow him?
Because I have my seminar open.
Yes,
Yes,
sir.
sir.
Permitted,
Just
sir. Sir, please share the screen, sir. Please. Hello. Am I audible,
Hello.
sir?
I'm just hoping my screen is shared. Are you seeing it clearly?
No, sir.
Okay. Screen. Is
Yes,
it
sir.
sharing now?
Yes, sir. Visible, sir.
Excellent. Thank you very much. Yes, thank you for the kind introduction. And yes, I've been with Sartorius a number of years now and have a lot of experience in different areas, including mass metrology. And I've been lucky enough on, I think, at least 3 occasions to visit India and to make presentations and to visit several of your mass labs, including the National Laboratory, and also to visit your legal metrology department. So I think today is interesting for me to be able to present to you. And normally I have a live audience in front of me and I get lots of questions coming during the presentation. So I will try my very best to explain everything carefully because I can't see your reaction, and I will do my very best to make sure that all of the content you can understand. I think there will be a time at the end for any questions, and we can go through the points that you'd like to discuss then. So what should we discuss? Well, one of the many questions that we get from even our own Sartorius people, is it a balance? Is it a mass comparator? What are the differences? And we will look at that very closely. Then we should also look at the applications of mass comparator and the different types that you will be able to find in your laboratories. Then we should look at terminology, because there are lots of terms that we use in mass metrology and that need to be explained and understood. Once you have in your pocket all of the correct terminology, then we can use these terms in applying the correct methods for checking the performance of your comparator in the laboratory on an annual or at the beginning basis when you're setting it up to install and to validate it. And then we will look at the actual requirements in the process of traceable mass determination. And as I said, we have time, I think, at the end for some questions, and hopefully we can get all of the answers for you. So, yeah, the question is, one of those is a balance and one of them is a mass comparator. There are some main differences, and normally I'll ask you to try and let me know, but maybe I can put some of the answers in myself. Well, I use a balance in my lab. Can I use a mass comparator in my lab? I don't know. Oh, well, what about, is this color of the screen looks a little bit different maybe. So I don't know. The mass comparator seems to weigh, but well, no, let's have a look at maybe what the real answers are. So first of all, in a typical laboratory, there are a range of balances and they're all used to measure net mass. So for example, you'll in a typical chemical or pharmaceutical laboratory, you may put on a small beaker, zero it out, add some component, and then you read off from the display exactly how much that you've weighed out into your container. So that is measuring net mass. A mass comparator, we don't do that. We never write down the actual result on the display of an object. We are normally using it to measure a small difference in mass. So we would, for example, have our reference weight and our test weight that we're looking to calibrate. And we use the comparator to measure the difference between our traceable reference weight, and that's very important, traceable reference weight, and the customer's weight that's being calibrated. So all we're using the comparator for is to very precisely give us the difference between a traceable reference and the weight that we're looking to calibrate. And because it's a mass comparator, we're able to do that with more resolution, more readability. So, for example, in the laboratory, we would find the best laboratory balance will be somewhere between 3,000 and 22 million steps between the first displayed value and the maximum range. So, for example, a model here, MCA225S, it has 220 grams readability with 5 decimal places. So from seeing the very first digit appear at 0.00001 until we reach 220.00000, we have 22 million steps. That is the best resolution we get in a laboratory. And for example, a kilogram, the best we can weigh out a kilogram of component would be 1 milligram. On a mass comparator, we can have as much as 111 million weighing steps compared to 22. So this is a very big difference. And you could find this on a model MCM 206, where it has 111 grams with a readability of 6 decimal places. So that's 111 million steps. And on a mass comparator, you'll find one of these models actually at the National Physical Laboratory, NPL, in New Delhi. We can actually measure small differences at a kilogram with 7 decimal places. So you can see a mass comparator is basically an instrument that is used to measure differences in mass, but with a lot more readability than you'd ever find on a standard laboratory balance. On a laboratory balance, you always have a full weighing range. That is from 0 to the maximum. You can see every digit displayed. On a mass comparator, mostly in the manual, their full weighing range, or they could have what we call a range window. And I will explain what I mean by a range window a little bit later. All the electronics of a laboratory balance are usually built inside. With a mass comparator, which you see here on the right-hand side, we have a separated electronics control box with the display also. So any heat that is generated from the electronics or the display are not interfering with the weighing system. Also, on a laboratory balance, there is something known as auto zero or zero tracking. And it's a little feature that makes your balance look quite nice. So when it's being tared to zero and it's sitting on the bench, it may want to drift a little bit up or down as the temperature in the lab is changing, but this auto zero function just keeps the balance at zero. It's like this little guy inside who is pressing the tare key. On a mass comparator, we don't want that. We want to have the drift because we correct for the drift mathematically. And I'll explain in some nice slides later how we're correcting for the drift. So in that case, with a mass comparator, the standard setting is 0 or zero tracking is turned off because we normally put on our reference weight, press the tare key, and then put on our weight that we're calibrating and measuring the small difference very close to 0. So we don't want the auto zero function from trying to correct our display. The repeatability of a balance, we do a repeatability test, and I'll explain that again later. But on the mass comparator, we determine with drift correction the repeatability. And when we get to the more expensive automatic mass comparators, they may have a load alternator, which is automatically loading the weights for us. And on the vacuum comparator at NPL, we're able to make comparisons in vacuum because the smallest amount of difference that we're looking at a kilogram with 0.1 of a microgram, we can't make a correction for air buoyancy that has a lower uncertainty than the difference we're looking for. So the mathematics we can remove by weighing in a vacuum, and we don't have any effects of air buoyancy. So those are some of, or all of the differences really between a standard laboratory balance and the mass comparator. So just to summarize, the definition of a mass comparator is normally a full range. Mass comparator it's basically a balance, but it has the best possible resolution, the best readability, which we've already discussed, and also excellent repeatability. We use it for determination of the smallest differences in mass. We can occasionally use a mass comparator for general weighing applications, but only for weighing very small amounts, particularly of valuable samples, perhaps measured against a heavy tare loads. So, for example, weighing small amounts of gas into heavy gas cylinders where we're measuring only a small amount, a mass comparator can be used for such applications. So that really fits in with small amounts being added as part of a formulation process. And then we have the range window mass comparator, which are really only ever used for calibrating weights or mass determination. We'll explain more about that a little bit later. So where are we going to find mass comparators? The main application for calibrating weights means you'll find mass comparators in the National Metrology Institutes, NPL in India, the PTB in Germany. We also name in the UK our national laboratory, NPL. Then we have regional laboratories in your country, India. I've visited several of the regional laboratories. Then also we have some private mass labs that are working maybe not just with mass, but maybe temperature and volume. And of course, if there are any weight manufacturers, they also need the mass comparators to be able to test the weights when they're first manufactured, and again when they're adjusted. And globally, the area of that we work with in the rest of the world is OIML, whereas in the USA, they have their own standard they follow, which is ASTM. And in the OIML, everything is incredibly well described. There are a lot of complicated calculations, which are all laid out quite nicely, and explanations are given for the process itself of calibrating. And in the OIML, we call out the weights that are being tested. We give them the letter B, and the traceable mass standards, our reference weights, we give them the letter A. And when we're comparing, we can either use the sequence where we put on the reference, we put on the weight being calibrated, which is B, and then again the reference weight. Or in some cases, we do it in the sequence where we put on the reference weight A, the weight we're calibrating B, we take it off, we put it back on again, take off the weight under test, and replace it with our reference weight A, ABBA. And there are reasons why we use the first or the second method, but a little bit more about that later. And this process of ABA or ABBA is how we determine the difference in mass between the reference weight A and the weight being tested B, and how we use this sequence to determine and eliminate any of the drift that we might see in the mass comparator. We also have to remove any influencing factors causing measurement errors, because there are a number of factors that can influence, and they're quite largely down to the design of the laboratory, the location of the mass comparator within the laboratory, and we have to minimize all of these effects of temperature change with climate control. We don't obviously want our mass comparator next to the window because of the influence of sun shining through. And at the end of the whole process, we have to find the total determined errors. This is what we call uncertainty, because in the OIML, we are given a maximum value for all of the cumulative errors in the process, and we must be within those limits that are given in the OIML, or for the Americans, the ASTM regulations. And very important is the uncertainty belongs to the process. The mass comparator contributes a small amount towards this, but the overall process of managing the calibration of your weights includes several areas which we will follow towards the end of the seminar, how we add all of these errors together to come with the combined total uncertainty. But it belongs to the process of the calibration and is not belonging just to the mass comparator. So you may be familiar with typical types of manual mass comparators. Again, mostly they're having separate displays from the weighing cell. And for a manual mass comparator, the best readability would be 0.1 of a microgram. And this would be for calibrating at the E1 or E level of weights classification from a milligram up to 5 grams. Again, a 5 decimal place mass comparator, in this case for calibrating up to 1 kilogram. And for the larger weights, which are maybe 10, 20, and even up to 50 kilograms, models all look the same, much larger weighing platform. No draft shield, but on such an instrument, an external draft shield can be added for the higher classes of calibration. Okay, so let's first of all look at how we might manage using manual mass comparators. It's possible with enough mass comparators to cover the range, even at class E1, we can calibrate weights all the way from 1 milligram up to 50 kilograms. We may need several mass comparators to cover that range without leaving any gaps. And if we're calibrating E1 or E2 weights, we would also need to make an air buoyancy correction. So you may have an external climate station, or some of the newer comparators may even have a climate sensor built in, so they're able to measure temperature, humidity, and air pressure in order to calculate the current air density, and will make the correction. If there is metrology application software integrated in the mass comparator itself, you would be able to enter the value of your reference weights, their uncertainty, follow the procedure of the software. If it's calibrating E1 or E2 weights, then even the air density calculation is made, the air buoyancy correction is made, the uncertainty can be determined and calculated, and you will get at the end a pass or a fail indication on all of the areas. So manual comparators are great, calibrate in the range 1 milligram to 50 kilograms, even at the highest class level of E1. Maybe there could be some disadvantages. Using manual determination, well, yes, the repeatability depends on the skill of the operator. It's the same in any instance, whether you're using a mass comparator, whether you're using a micro pipette, whether you're entering the Olympic Games in shooting at targets. The skill that you build up is helping you to reduce the errors. The way that you load the weight, the amount of time that keep your hand within, and the chamber can affect it. Here you see the lady, she has a special fork to load the weight, which keeps her hand outside. Being able to load the weight in one go, because the last thing you should be doing is to load the weight slightly out of position, and you should never try to pull the weight back, as this can shift the 0 point. If you don't have the time sequences between loading A and B and again A, uniform, the drift is not uniform, and the calculation to remove the drift is not able to remove the drift effectively, and this results in a higher repeatability. Mixing up of the weights. Let's hope it doesn't happen in your lab. There's always the story where, because of the sequence ABA or ABBA, someone accidentally put their reference weight back into the customer's box of weights and kept the customer's weight. So if you do this, then it's a little bit of a catastrophe. So the other thing, of course, with the OIML description now, all weights in class E1 or E2, the very small milligram weights, all have to be made of wire. And when you get down to 1 milligram, it is really difficult to load and unload that 1 milligram wire weight using a manual comparator. So looking at this, you can see now all of the points I covered. Of course, it's lower initial cost than using automation. It's really easy to install a manual comparator. It's basically the same as installing a laboratory balance. You're able to unpack, assemble the draft shield, put on the weighing pan, switch on, and within several hours it's equilibrated and it's ready to go. And of course the servicing costs are lower. Normally a local engineer can check and make minor adjustments. If you change your laboratory or you want to move the mass comparator, generally there's nothing difficult, no adjusting of the weighing system for transport. You simply switch off, move the comparator, and it relocate to the new position. So there are the advantages. So automation, a lot of mass laboratories are moving in this direction. And here you see two examples. On the left-hand side, you have a carousel type mass comparator, in this case 1 kilogram, and the readability 1 microgram, and up to 16 weight positions. So this means you can load, for example, if you have a box of 1 kilogram weights, you could load all of the references, the 1 kilogram, 500 gram, 200 gram, 100, a 50, a 20, and a 10 gram reference. And then you have enough space to load the rest of the weights that are being tested, the 1 kilogram, the 500 gram, and of course, in an OIML set of weights, you will have 2 times 200 and 2 times 20 grams. So you have enough space on an automatic machine like this to load a box of weights. It will calibrate, and then you have your results saved in a file. Other alternatives are what we call robotic mass comparators. And in a robotic mass comparator, in this case, for example, you could have as many as 120 weight positions in the magazine. The robot is able to collect the weights, take them to the mass comparator, both the test weight and the reference weight, and simply alternate between the test weight and the reference weight. Big advantage there is the number of weights you can use. And for the mass laboratories that are performing dissemination, maybe some of the larger regional laboratories or in the National Physical Laboratory, it's even possible to build up a set of 4 weights to compare against a single weight for weighing by substitution. So the robot is the most flexible. The next option is a carousel-based automatic mass comparator. So in a carousel-based system, they're extremely flexible. The weighing schemes, you can decide whether it's ABA or ABBA, how many cycles you'd like to run. And the latest mass comparators, you don't have a standard laboratory balance display. You connect using a laptop or a PC with the web browser, and it's a web services user interface. So the turntable holds the reference and test weights. The turntable rotates to the program position because the mass comparator is sitting just underneath one position. It gently lowers the weight. So you've put all of your weights onto the carousel, told the mass comparator which weight is in which position. It will then compare position 1, which could be your 1 kilogram reference, against position 8, which could be the 1 kilogram weight being tested, for example. So the rotation happens, it lowers the weight very slowly and accurately onto the weighing pan. And as mentioned, a range of different mass values can be tested on the same instrument. Big advantage here is there's no human intervention. You load the weights and leave the comparator to do all of the work. So they work whenever you want them to work. If the laboratory is going to be more stable conditions overnight, you can program such a comparator to start after you've all left, when there's no one walking, when the doors remain closed, the temperature becomes more stable. And automatic mass comparators can be used for class F1 calibration, but also are ideal for the highest weight levels of E1, E2, or maybe even at the national level, E0, for example. So With automatic and robotic comparators, you can even load up to as many as 120 weights. And with the operator programming, these systems will run through the day and through the night and over weekend. So it's great that you can load an entire set of weights, all with different nominal values, and can be calibrated and adjust, and the results stored on in a file which you can extract and then produce the calibration certificates. The robotic comparators, again, are mainly used for the highest class of weight determination, mostly E1, E2, but also for F1 calibrations. The limiting factor for automation is that they become very expensive if you're trying to calibrate the M class weights or F2 class, because the cost to set up is much higher and it would be very difficult to have a return on investment. But mostly class E and class F1 are the weights that are usually calibrated on either robotic or carousel type mass comparators. Dissemination is also a feature for robotic or the carousel-based mass comparators, where you're comparing a series of weights against single weights. It's much easier once the weights are loaded in position for the automatic or the robotic systems to handle a group of weights than it is for lab technicians to try and load and reload in the same position 4 different weights. So let's start to consider some of the terms. We're going to look at what we mean by repeatability, how we calculate it through a drift compensation method. We need to look at linearity, and linearity is more important to know on a laboratory balance, but we'll explain why we still want to look at it on a mass comparator, because what we're more interested in is what we call range sensitivity. So all of these will be explained. We'll have a look at some other important specifications and how capacity and readability can be different on different types of mass comparator, where some have electronic weighing ranges and some have range window. So let's start with repeatability in this case. So repeatability, how we would do the test on a standard laboratory balance, just to give you an idea of the differences. In a laboratory balance, we need to measure the ability of the balance in the same testing conditions with the same test load. How is the balance able to perform? Is it able to give the same value or very close to the same value on a number of repeat weighings? So typically, if it's a 200-gram balance in the laboratory, we might use a 200-gram calibration weight, make 10 repeat weighings, and calculate the standard deviation. So it's a case of here, 10 weighings, write down the value, calculate the standard deviation, and that should be less than or equal to the specification given by the manufacturer. That's how we do the repeatability on a laboratory balance. If we did that on mass comparator, because there's more readability and more drift, then we probably wouldn't reach the standard deviation quoted by the manufacturer, because balances might have a small drift during measurement, but mass comparators will have a bigger drift. Could be 10 times higher, because it will have at least 10 times the readability. So in that case, how are we going to make the sensible estimation of the repeatability on our mass comparator? Well, I've already hinted a little bit earlier on, and it's a drift compensated standard deviation measurement cycle, ABA or ABBA. So this is what we are going to look at, how we are making the test. So for the mass comparator, we want to make sure that we get the results again under standard testing conditions with the same load placed on the weighing pan in the same manner, as close as possible to the center. And usually the mass comparators have some circles marking to give you a little help in where to place the weight. So we perform normally 5 cycles of either a BBA, where it's reference, test weight, and reference weight, and we calculate the first difference. We then calculate the second difference, the third, the fourth, the fifth, or the sixth. Sometimes with automatic comparators, we may do 6, but usually in specifications it's 5. And the same here, a BA, first, second, third, fourth. And from all of these differences, we can calculate the average difference and then the standard deviation. So automatic or robotic, it's the ABBA. Manual comparators, we use the sequence mostly ABA. Why do we prefer to do ABA on a manual, and why do we prefer ABBA on an automatic? I can see you're thinking, please tell me why. So, okay, with the automatic or robotic mass comparators, we have even higher readability or better resolution than we would with a manual comparator. So we can use the reference weight with its test weight, and when we place the reference weight on again, we have another value for the test weight. So basically, in the first difference, each time we place the reference weight, it has its own B. So each A has its own B that is being compared against. So this A is compared against this B, this A is compared against this B. And because there's more readability or resolution, there may just be a little bit more drift. And when we're correcting and subtracting A from B, and this A from this B, they have their own differences. In a manual comparator, it's not always possible to take the advantage of an own B for each A, because the resolution is lower, the drift is lower, and therefore we don't get any advantage in getting a better repeatability using ABBA instead of ABA. Got some calculations and a few little graphs to explain this in more detail. So here you see for ABA, put the reference weight or the standard, the test object B, and then against the standard. And we want to keep this in the same time sequence as possible, so that any drift that happens between here and here should be the same as from here to here. So we don't want, for example, having taken off the reference, to place the test weight within 10 seconds, take it off, and then wait 30 seconds before putting the standard, because then any drift that might happen here is going to be bigger than the drift here. So this is one cycle with 3 actual measurements, 3 weighings. So as I mentioned, with the sequence on an automatic or a robotic, the differences are independent. Here we share the differences between the reference and the test weight. Both methods you'll find in the IML. Both methods give equivalent uncertainties on the same type of comparator if the number of weighings are equal. So you see, for example, here, if we do one cycle of ABBA, we have the number of weighings would only need to be 3. If we were to do ABA, we would have to do 5 cycles to get the same repeatability. But normally with an automatic machine, we're looking at the highest weights, E1 or E0. So therefore, we can get a better repeatability with less measurements. Now, in the IML, they will actually tell us. So if we want to calibrate an E1 weight, ABBA, we only need 3 cycles of ABBA. With the manual comparator, we would need 5 cycles. E2, we could reduce on the automatic to 2 cycles or 3 cycles on the manual. So you can see if you do ABA, you need a few more cycles to reach the required repeatability needed to keep the total overall uncertainty within the limits. There is one other method, rather than ABA or ABBA. Usually we use this for the lower classes of weights, the M class, where we do A and we put our test weight B on again, and then finally at the end, the reference. Because we can tolerate a little bit more drift when we're calibrating M class weights, so there's no need to go A, B, A. We can just go A, B, 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 and then A again. I hope that's clear for everyone. So let's have a look here at how the calculation is done. So we put our reference weight A onto the mass comparator. We put our weight being tested, B, and then we place our reference weight again. So this is A1, B1, and A again, so it's A2. So what we do in the calculation is we add together the value we get for A1 with the value we get for A2. And we have to half that because otherwise it's going to be double the value of the weight we're testing. Then what we do is we subtract the half value of A1 plus A2 from B1, and we get our first difference. So we add the reference first measurement to the second measurement divided by 2, and we minus that from B1, and that gives us the difference in value between the weight we're testing and our reference weight. We can do a second cycle, a third cycle, as many as we need, and then we look at the number of differences that we have, and we take the average of those differences to give us our true difference between the weight that we're testing and the reference weight that we're testing it against. And from those differences, we can then calculate the standard deviation, which gives the repeatability. So it's the mean difference of all of the weights being tested in the different number of cycles. I've only shown 2 here for ease. So just to make this, I like pictures. I like to be able to see something explained with a picture. So just to explain how drift correction is working with ABA. So in this case, we're going to just assume that we have 2 weights that are perfectly 1 kilogram with 2 decimal places. So we place on the weighing pan our reference weight A, and at this point there's no drift. So we get on the display the value 1000. We take A off and we put on B. And in that time, in this case, in my example, the comparator has drifted by 1 digit. So the value we get is 1000.01 because we got a positive drift here, which is added on to the actual value, which is the yellow color, and we get an error. Then we take off B and we put A back on again. So we get the second value for A, and the comparator is drifted by another digit. So in this case, we see on the display 1000.02. So if we add A1 to A2, in that calculation we have 2 digits of drift, but when we divide it by 2, we have only 1 digit. So 1000.01 minus 1000.00 plus 1000.02 divided by 2, it's 1000.01, which is B, minus 2002 divided by 2, it's 1000.01 minus 1000.01. So the value we've calculated for our weight being tested is exactly correct. So this is what we mean by drift correction. We allow the drift to happen. We're measuring the drift because each time we put A or B back on, if there's any drift in there, we add these two together, divide by 2, which halves the drift, which is equal to the drift that we see in the weight that we're being tested. Does that make sense for everyone? Hopefully we've explained that nicely. So when we're calculating the repeatability in the weighing process, or if we're just testing the comparator in use, we want to just be sure that our comparator is still working correctly. In the test that we do, we could actually just use the same weight for A and B. We don't have to have 2 different value weights. We can just use the same single weight. It just makes it easier. So A, B, and then A again. It doesn't matter if they're both the same weight because the calculation will take out the drift in exactly the same way. You get a value, a second, a third, a fourth, and a fifth, and then calculate the standard deviation. So, linearity. Now, in a laboratory balance, the manufacturer will give a maximum value for linearity error. So it could be a positive or it could be a negative. And in this case, we've got what looks like a nice, perfect red line, theoretical, from 0 to the maximum. However, on the laboratory balance, we placed some test weights at different positions, and we found, yes, there's some errors here and some errors here, and round about here, it's okay. So we can prove on a laboratory balance, if this value deviation is no more than the specification, then we're happy the balance is working. Because if we weigh anything in the laboratory, it's okay because that will not affect our result. It's within specification. It's not going to affect the calculations for any assays that are done because it's well within the tolerance. So that's the maximum deviation between 2 points. If if we look at this on a mass comparator, it doesn't matter, because what we're interested in is how much difference is there between A and B. And both have the same amount of linearity error. So when we're only looking for a very small difference between A and B, they both have the same linearity error, because in such a small difference between the reference weight and the test weight, you won't notice the linearity error. If you're simply weighing the weight, then you would have this total error. But when you're comparing A to B, you've got almost no error. It's almost not measurable, the change in slope between here and here. So what we look for in a mass comparator, we call this range sensitivity. The difference on the actual slope between the reference and the test weight is almost, if not completely, negligible. So this is what we mean, range sensitivity between A and B. So for example, on a particular comparator that has a readability of 7 decimal places, the range sensitivity, the linearity error between A and B, the maximum should be 1 milligram. So this is the range sensitivity. It's 0.1 of a microgram in 1 milligram. So if all we're looking for is a difference between the reference weight and the test weight, a maximum of 1 milligram, which would be quite huge anyway, it will always be less than that, the maximum deviation we're going to see is 1 microgram, because a 0.1 microgram. As we said, the range sensitivity on this instrument is no more than 1 digit when there's a difference between the test and the reference weight of a milligram. So when they're between A and B is a milligram, the maximum error you'll see is just 1 digit, which is 0.1 microgram, which is negligible. So we never worry or need to think about linearity in the same way in a comparator, because we're not making absolute measurements of mass. We're looking for very small differences where the error in that range is more or less only the same as the readability. It's sometimes a difficult one to explain, so I've tried my best to explain what we mean by range sensitivity instead of a linearity measurement. So what else is important? Stabilization time. Of course, you don't want to be waiting 10 minutes for the comparator to show stability, and quite often with weighing instruments, the mass unit disappears when it's unstable and appears when it is stable. And quite often in mass metrology, we use this stability indicator to give us the moment when the comparator is more or less stable. If you have a comparator with a glass draft shield and maybe 4, 5, or 6 decimal places, when the door closes or you've taken your hand out, there could be just a little bit of air movement. So mostly people, when working in a mass calibration laboratory, don't take the first reading as G appears. G appears, which is the gram, or mg for milligram. Count a few seconds, maybe 5 seconds. Do that for every measurement and you get a better value. It may just change by 1 or 2 digits in that 5 seconds as the air is still moving in the weighing chamber. So stabilization time is always given. You should reach that. If you don't, then there may be some vibration or other disturbance in the lab. Nice is to see the stability indication and wait maybe 5 seconds, then take the value. Because the comparators share the same software as laboratory balances, there are 4 levels of adjustment for vibration. I would say with a mass comparator, it's set at the optimal setting for working in a mass lab. There should be no reason to adjust the digital filter to filter out vibration. Normally, as it is, it's correct. We also quote a sensitivity drift, which is what you might expect to see in the drift of calibration for every temperature change of 1 degree, and maybe a 0-point drift, which is the electronic drift. But again, both are taken out in the ABA cycle. Manufacturers will typically tell you the maximum temperature you should work in and the minimum. So in a laboratory for manual, it shouldn't be colder than 15 degrees or warmer than 30 degrees, because outside of these specifications, you get a higher drift on the comparator, and for the automatic models, between 17 and 27 degrees. Optimal would be 21, 22 degrees if you can maintain the laboratory at this level. So let's look now at the different types of mass comparator. Most electronic comparators today have a continuous range, so they appear to work like a balance. So from 0 to maximum, you have no difference on the display. It just simply shows you a full range from 0 to maximum. There's no other symbols, no other changes necessary. It's also possible to have what we call a continuous range, but with a substitution weight. Yes, what does that mean? Well, I will explain in the next slides. It appears to be a continuous range, but it's not quite. And then in the beginning, when electronic balances had a limitation on resolution, all the first comparators, even the manual ones, were what was known as range window, or some of the highest specified manual comparators, and mostly all of the automatic comparators work with what we call a range window. I've got some nice slides to show what we mean. So this particular model, it's an MCM 605. It has a maximum display capacity of 610 grams, which means that when you start from 0, any value that you put on the weighing pan, you will see a value in the display all the way up to 610 grams. With your OML weights, it'll be 500 grams, but in the USA, ASTM, they do have 600 gram weights, which is why such a comparator has a range of 610 grams. But a continuous range means you can see every value directly displayed. So same readability, 5 decimal places, but you can have a mass comparator MCM 1005 where the maximum value you can compare of weights would be 1100 grams. But due to restrictions on resolution, it's not possible to have a continuous range electronically of 1100 grams. So it has the same electronic range as the previous mass comparator, 610 gram. However, when you switch on the mass comparator, there is actually a 500 gram substitution weight inside of the instrument sitting on the weighing system. And when you place any weight on the weighing pan up to 610 grams, you see you're weighing within the electronic range of 610 grams, because this comparator actually needs a kilogram to make it work. So we've got our 500 gram external weight and the internal substitution weight of 500 grams. So in this first part, it's working totally electronic. So you take your A off, put your B on, and you're just working in this electronic range. So if we want to then test a 1 kilogram weight, you place your 1 kilogram weight on the weighing pan, and on some of the later models of mass comparator, there's a motorized system that lifts off the internal 500 gram weight, and you see now this electronic range is working from 610 grams through to 1100 grams. So for convenience, the motorized switching of the substitution weight makes it convenient, and you don't, in many cases, even realize that's happened. So this is what we mean by continuous range, but with a substitution weight. So some of the older comparators, the substitution weight, you have to switch by hand. There's a little rotary dial. With the earlier comparators, the substitution weight may have been actually external, and here you see it sitting at the back, hanging on the 2 pegs, and this substitution weight is either placed back on the pan or taken off the pan. But now with the latest system, it's integrated in the weighing system and it's switching itself automatically. Now, the highest resolution automatic comparators, or the older, very early electronic comparators, had what was called a range window. So the first type is a continuous range from 0 to maximum. Second type is continuous with substitution weights. And the third type now is a range window instrument. So here, it only has a very small electronic range. And on this comparator, if there's nothing loaded on the pan, you just see the letter L. You put 50 grams on this particular model. It's a model C50. So its maximum capacity is 50 grams. We put the 50 grams on of our A, take it off, put on our B, and we can measure in a small window, maybe a few grams either side, we can measure the difference. Now that works for 50 grams. If we want to test a 20 gram weight, then this comparator would need an internal substitution weight loading of 30 grams. We would still see L until we place our 20 gram reference on, and then we've got again this window because the total weight is 20 grams on the outside on the weighing pan and an internal substitution weight of 30 grams. So we're able now to compare 20 gram weights. And again, if we want to test a 10 gram, we have two internal weights, a 10 and a 30 gram. And until we place the reference weight on, we just see L on the display, L for low. We put the 10 gram reference weight, and then our combined value, we can tear off the 10 grams, take off the 10 grams, put on the test weight, and measure the gain, the small difference between the test weight and the reference weight, which will be within the range window. Or sometimes these weights could actually be applied externally as well. But mostly you won't see now many manual mass comparators that have such range windows anymore. It's either continuous or continuous with an internal substitution weight. So there you see, just to summarize, if you want to compare 10 grams, we have internally 30 grams. Compared 20 grams, we have internally loaded a substitution weight of 30 grams. And for 50 grams, we just simply have the 50 grams on the weighing pan. So now comes to testing our parameters. Which parameters do we test? How do we test these parameters against what are the manufacturer's specifications? So, repeatability test. We've already mentioned we're going to have some drift. So we, on our manual comparator, would follow the ABA method. 5 cycles would be what the manufacturer would normally quote. And I did mention earlier that when you're testing the repeatability, it's acceptable and it's easier just to use the one weight for both A and for B. You do, the repeatability is tested at the nominal load. So if it's model MCM66 with a 60 gram maximum, you're going to be testing 50 gram weights as the maximum. So you need to be testing the comparator at its nominal, which is the most difficult to get a good repeatability with a heavier weight, and at 5 grams at 10%, but nothing less than 5 grams or 10%, because much below there, you then bring in difficulties for the comparator because it's not able to test lower weights because its own repeatability compared to the smaller mass is not good enough. So always test it at nominal and then perhaps also at 10%, following the ABA drift compensated method for 5 cycles. Calculate the 5 differences, which ought to be fairly close if you're using the same weight for A and for B. Calculate the standard deviation, and that is your drift corrected repeatability. I did mention that linearity is not critical for a mass comparator because we're never weighing anything, but it is a test to ensure in the end of manufacturing, and maybe you want to do this yourself in the lab, just to check that the weighing system performs adequately. With a mass comparator, the resolution is much higher than a laboratory balance. And if you were to use up to 4 weights on the pan together to test the linearity throughout the range, the cumulative errors on those 4 weights could be bigger than the linearity error that you're trying to measure. So with this in mind, and it's also done in this way in the laboratory for standard microbalances. So in a laboratory where they have a 5 gram 6 decimal place microbalance or a 2 gram 7 decimal place microbalance, again, they don't place a series of weights on. They use what we call the step-by-step method. we only use one weight to make a measurement, and we tear off other weights so that we can move through the range. So, for example, I've not put any values on this because it would be the same method whether it's a 500 gram, a 5 kilogram, a 10 kilogram, or a 50 kilogram manual mass comparator. We would put our first weight on the weighing pan, record the result, and that should be within specification. We tear off the first weight, so we actually have 0 on the display, but then we place this weight back on again and record the value, and again it should be within specification, but we're actually testing at this part of the weighing range. We take it off, we add another test weight on, tear it back to 0, so it's a tear weight, and then we put the same weight back on again, and we measure its value at this part of the range. And finally, we tear off enough mass so that we can test it at the nominal. So we've only used a single weight, but by tearing off, we haven't added together all of the uncertainties of these 3 test weights plus the uncertainty of this weight. We're only ever having one uncertainty of the high quality weight that we're using to test the linearity throughout the range. But as I mentioned, more important for us is the range sensitivity. So if you added 4 weights together, the tolerance of the calibration weights would be greater than the readability of the mass comparator, which is why we only use the 1 weight and tear off other weights to bring the measurement of the single weight in this range, and to the nominal level. So yes, the errors, if we put 2 weights, 3 weights, 4 weights, the total errors would combine, and the total combined errors would be greater than the value we're looking for in the linearity test. So on this model, at 60 grams by 6 decimal places, or 0.001 milligram, the error we're looking for at any point on the curve is 0.008 milligram. So if we added together a 1 gram, a 5, a 10, and a 20, these are the tolerances of those weights, class E1. We've already got a total tolerance error almost 10 times bigger than the value we're trying to measure. So that is why we would never put on a 1 gram, add a 5 gram, add a 10 gram, and add a 20 gram and write down the values, because at each point we're adding together the tolerance errors, and the sum of the tolerance errors is almost 10 times bigger than the linearity error we're trying to measure. So this is why we use 1 weight and tear off to allow us to then test at these values. So what's more important for us is the range sensitivity. The likely error to be found between the difference, the maximum difference you could find between your reference weight and your test weight. So the way to do this would be to use a single test weight combined with a very small 1 milligram, and then you can measure the difference once tearing off your test weight and adding the milligram. you can then measure the difference, which probably is almost zero, if not zero, between the reference and the test weight. So only use a single weight, which could be a 2 gram or a 5 gram or whatever is typical for a part of the weighing range. Add your 1 milligram or 5 milligram, whatever is appropriate for the value of the comparator. Record the value and it should be within the tolerance given here. So range sensitivity is more important because we don't want the comparator to display an error between the level of the reference weight and the maximum deviation for a test weight. So because the reference and test weight have almost identical mass, the sensitivity is negligible. So you may choose not to do a sensitivity test. It's not critical. It's not absolutely necessary because linearity is something, once you've tested it, it doesn't change throughout the life of the comparator or through the daily working of the comparator. Temperature change has no influence on linearity or range sensitivity, where it will have a difference on the absolute calibration. So it's not so critical to do on a regular basis a sensitivity test. Eccentric loading error. It would be great if you could place your weight anywhere on the pan and see the same value. It's not going to be the case. There will be some slight differences. There are some rules to follow on a mass comparator compared to a laboratory balance. With the laboratory balance, we might test it with half its maximum load and possibly half the distance between the center of the pan and the edge of the pan. In a mass comparison, we don't really want to stress by testing at this distance. We want to test within the range where we'd normally place our weights. So for a mass comparator, whether it be a rectangular or a circular pan, we start in the center, and for convenience, we quite often tear. We take the weight and we place it within the circle that we're looking for the size of the weight to compare. So it must be within a maximum of half the nominal. So if the comparator is 2 kilogram, no more than 1 kilogram for making the test. And the testing for these positions 1, 2, 3, 4, and 5 must be within the circle for the size of the weight. So if this was a 2 kilogram comparator, then this circle, the inner circle, would be defining where the 1 kilogram weight would be placed, and the larger circle for the 2 kilogram weight. So if you're testing at half nominal, you'd use a 1 kilogram weight, place it at the center, move it slightly to position 2, to position 3, position 4, and position 5. Do not try to test the corner load outside of this area. The large pan is for convenience, but it's marked for where you should be testing cylindrical weights. And in the OAML, they do tell you if you've determined the corner load, it doesn't necessarily have to be added in to the combined uncertainty, because in the process of doing 5 ABA cycles, you already have the corner load incorporated. So in most cases, they say the uncertainty contribution is already covered by the uncertainty in the weighing part of the weighing process and may be neglected. So these are all from quotes from the OIML. So you will clearly see on all the comparators markings of where to place your weights. So this is a nice question. We always test and adjust the calibration of our lab balances. So in a pharmaceutical lab, they will have an SOP, standard operating procedure, which tells them whether it's daily, weekly, which weights to put on, check the calibration. If the balance is out of calibration, they have to make an adjustment. So do we need to adjust the calibration of our mass comparator before each test? Well, I'll give you a clue. And the clue is no. We're not interested in the mass comparator weighing accurately because test weights are compared against certified and traceable reference weights and are not determined by a weight value indicated in the display. So ultimately, the calibration of our mass comparator is not critical because when we put our reference weight on, its value is known precisely and the uncertainty of its value is also known. So it's not necessary, and although a lot of people will do it anyway, there's an internal adjusting weight on most comparators to allow this to happen, but it's not hypercritical because you're not weighing, you're comparing. And we know exactly and precisely the value of the reference weight. Therefore, it's not absolutely essential to have the span of the mass comparator adjusted for each time we're making a calibration of a test weight. So this is what a typical range of comparators could look like for calibrating between a milligram and 50 kilograms. Mostly the smaller comparators have a draft shield. The larger ones, if you're calibrating M class, it's not so critical. But if you're calibrating F or E class weights, you can then purchase a second external draft shield. So for those people only calibrating M class, we don't ask you to purchase in the beginning. Mostly this type of comparator you buy then afterwards or together a second external draft shield to prevent any air movement from influencing the process. So next, what we need for calibration. Process, what we need for the uncertainty calculation, what we need for air buoyancy, and then finally we will summarize and we will have a time for some questions and hopefully the answers. So in a mass lab, first we must have stable climate control. So the building and the room that's been allocated for the mass lab need to be of sufficient standard to reduce vibration to maintain the temperature. We then need a user, a metrologist with sufficient knowledge of what he's doing or she is doing. We need a traceable reference weight. We need suitable comparator because in OIML, you need no more than 1/5 of the permissible tolerance as the total error in the weighing process. If you're calibrating E1 or E2, you'll need some climate sensors for temperature, pressure, and humidity. You may write down the results, you may have them printed out, or you may have some software either integrated or in a PC. It could be a commercial software, or it could be an Excel spreadsheet that you've created yourself and place the values in, and the calculations can be done. So at the heart, you can have a mass comparator. It may be that the comparator with its own integrated software can handle the uncertainty calculation because it's measuring the temperature from the climate sensors. You can have your own database, perhaps, if the comparator is capable, stored within, and you can have user management to determine who is using the comparator by logon. So these are what you really need in your lab. But let's hope it doesn't look at all like this, because all of these factors will influence severely the performance of the mass comparator. We need air conditioning for sure, but what we don't want is an air conditioning system that simply blows cool air directly, switches off. When the temperature rises, it blows cool air again. If we can have a filtered system where the air is trickling from the air conditioning system, and certainly we don't want the comparator in the line of the air conditioning system. Ideal would be to have no windows in the lab, because the sun shining through the window will change very quickly the temperature within the laboratory. And we certainly don't want a lot of people walking through and opening and closing the door, because that will then again allow temperature changes, vibrations. There are some really great stone tables now. You can either build your own or you can purchase. Ideal would be if the floor in the lab was separate from a small plinth of maybe concrete that this table can stand upon. So the two worst enemies for causing instability are drafts or low frequency vibration. A motor going pump, 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 very low frequency. And the digital filter in a laboratory balance or a mass comparator is so advanced today that normal effects are removed. However, the low frequencies, so again, if the floor is bouncing, or you have a motor, or you have a drift, a low frequency effect is indistinguishable from you adding a small amount to the weighing pan. The digital filter cannot differentiate between a low frequency vibration and a small addition to the weighing pan, and therefore these have the biggest influence. So the requirements for traceable mass calibration is a reference weight with a calibration certificate. We need an accuracy class of the reference weight to be one level higher than the weights we're testing. So if we're calibrating E2 weights, we need E1 references. If we're calibrating E1 weights, we need weights that have a better uncertainty than E1. So it needs to be lower uncertainty, because if you make a calculation for the total combined uncertainty and you've used the same class of test and reference weight, the contribution to the uncertainty from the reference weight will be too high. Even if we keep all of the other levels at the right level, we will fail on the combined uncertainty because we've used a reference weight of the same level as our weight under test. We need to know its nominal mass and its conventional mass, which will be on the certificate. Its uncertainty will be quoted on the certificate, and it will have been calibrated in the correct environment conditions. We will know that the density, and this will be on the certificate, or from the original manufacturer, this information is given together with the uncertainty of the density of our reference weight. We need a mass comparator, and we need to have our database of our reference weights. We need a climate station, or in some cases, it can be integrated into the mass comparator. And we need an application to follow for the mass metrology. So we know to make the calculations in the end to determine the conventional mass of our test weight with all of the errors known and the uncertainty calculated. Of course, we need a test weight. We should know its density and its uncertainty. We then calculate the conventional mass with the uncertainty budget quoted and the actual uncertainty in the whole process, the combined uncertainty determined. And if it's E1 or E2, we determined the environmental conditions with their uncertainties and made the buoyancy correction. So I'm going into the last part of the presentation now. So in the process, the norm that we're working to is what we're measuring against. In most cases, it's OIML, the Americans ASTM. We need to determine how we're measuring. Is it ABBA on an automated machine? Is it ABA on our manual comparator? What class are we calibrating to and how many cycles do we need? Adjustments are needed for air buoyancy correction for E1 or E2. So we calculate the air buoyancy, and by knowing the density of the reference and the density of the test weights, we can apply an air buoyancy determination. And finally, in the whole process, we have to determine the overall uncertainty, which is combined of type A from the weighing process and type B, the known uncertainties of the reference weight, the uncertainty in the buoyancy correction, and the uncertainty of the weighing instrument. And finally, we can calculate the conventional mass of the weight we're testing, and we need to be able to quote that together with a combined or expanded uncertainty, because any value you write down is only valuable when it's written together with the uncertainty. Climate values are monitored throughout the process. Ideally, it could be recorded for each ABA cycle. And we have a protocol to make the final calculations to complete the mass calibration. So I'm not going to explain all of the calculations. They're shown here for information. They're taken from the OIML, and these are the references where you will find the calculations. So most important to know is that the total uncertainty must be less than or equal to 1/3 of the maximum permissible error. So in the OIML table, for all weights, you're given a nominal value and you're given a maximum error that those weights, depending on whether they're E1, E2 or F1. So our total combined uncertainty must be less than or equal to 1/3 of the tolerance or the maximum permissible error for the weight you're testing. And I mentioned earlier that the smaller the mass you're looking to measure, the greater is the uncertainty contribution of the mass comparator. So the uncertainty you'll find on the mass comparator is constant, and this value you'll see has less influence as we approach the maximum value of the comparator, because it's a fixed uncertainty. The smaller the weight that you're comparing, the larger the contribution this has to the uncertainty contribution from the weighing instrument. So it's a fixed value which is almost negligible at the higher end, but when we get down, so we would never use a 10 kilogram comparator to calibrate weights in this range, because the uncertainty contribution, as you start to approach the lower part of the range of any mass comparator, has a bigger influence against the small weight that you're comparing. So for weights of this value, then we would have a comparator with maybe 50 gram maximum, and the contribution of the uncertainty then is lower. So we always have to make sure that the comparator that we're using is able to give an uncertainty contribution of no more than 1/3 of the maximum permissible error. So when we do our drift corrected ABA, the standard deviation we get should be no more than 1/3. So that's important to know, to choose the right comparator for calibrating the weights at either E1, F2 or whatever you're looking at. So by doing the uncertainty calculation, the repeatability calculation, we can be sure that the contribution from this particular comparator is no more than 1/3. So probably in this range, it's good to calibrate most of the weights down to 100 grams. But once we get below 100 grams, then its repeatability is not good enough to keep the uncertainty contribution below 1/3. So basically, the type A and type B uncertainties are coming from the weighing process itself. We have to calculate standard deviation there. We have an error on the certificate of the calibration weight itself, the reference weight. If we're doing an air buoyancy correction, then the different sizes of weight, volumes of weight, if the reference weight has a smaller volume than the weight we're testing, because there's a range of densities allowable, then it will have a smaller displacement of air than the weight we're testing, and the air buoyancy on this weight will be higher because it's displacing a bigger volume of air than the reference weight, and therefore we need to apply the air buoyancy correction. And of course, there'll be a repeatability error in the balance. So in the weighing process, we'll do our ABBA, and we will end up with a contribution to the uncertainty. The reference weight from its certificate will have an uncertainty value. So if we're putting this into our database, it's a class E2 weight. Its nominal value is a kilogram. The nominal value deviation here is 0.5 milligram, and the expanded uncertainty on the certificate we got with our reference weight, we're given here with a value which we can also use in the calculation, and the coverage factor is 2K, because whenever we get a standard deviation for the repeatability, we always take 2 times that value in the overall combined uncertainty. When we're doing the, I'm not going to go through all of these calculations, they're literally taken from the OIML, but we need to determine the uncertainty in the air buoyancy correction, because there'll be an uncertainty contribution from the, there'll be an uncertainty contribution from measuring the temperature, there'll be an uncertainty contribution from measuring the air pressure, and also a small uncertainty from measuring the humidity. So all of those are necessary for the air buoyancy correction uncertainty. From the balance, we have to add a value for the uncertainty due to the display resolution, the sensitivity, which is the range sensitivity. Also, eccentric loading, as the OML said, you don't have to add this because it's included in the process of making your 5 or 3 ABA cycles. And yeah, the uncertainty and the sensitivity of the balance is the difference between the test weight and the reference weight. Again, it's normally 0 or very close to 0. So, and there's always a slight error on a display resolution, because although comparator is showing a value of 4 decimal places, there is an invisible decimal place, the internal resolution. So for that to be a 2, this value in the next decimal place has to be below 5. But if it's over 5, then that would be a 3. So that you have between 0 and 4 on the invisible decimal place, it will be a 2. Between 5 and 9, it would be a 3. So there's a slight uncertainty coming from the display resolution. Corner loading error, we've mentioned. And these are the likely contributions in the air buoyancy. So your sensor will have an uncertainty for temperature, an uncertainty for air pressure, and an uncertainty percentage here for the humidity. So all of these are important parts to calculate the overall uncertainty from the air buoyancy correction. So we've done all our measurements. We have a calculation. We calculated the uncertainty, and in this case, we want to know, was this particular comparator okay for testing a 10 kilogram weight? And in this case, the 10 kilogram weight has a maximum permissible error, 12 milligrams, and the uncertainty is a third of that, which is 3.05 milligrams. So with E2, we're calibrating. The maximum error is 16 milligrams. A third of that error is 5. And in the process here, we determined 10 kilograms with an uncertainty of 12 milligrams. And we got the combined uncertainty here of 3.05. We're allowed 5, and 5 milligrams is less than 3.05, which means a test weight can be qualified on this mass comparator. This is proving that we're able, with a 10 kilogram test weight, we get the combined uncertainty of 3.05 milligram from our ABA cycles. And when we look in the table, the 10 kilogram E2 weight has a tolerance or maximum permissible error of 16, and a third of that is 5, and we reached an uncertainty in the whole process of 3.05 milligrams, which means this comparator has been successful in proving it can calibrate a 10 kilogram E2 weight, because the maximum uncertainty in the whole process is 5, and we reached 3.05. So that is the end. Just a few things that are helpful for you. Lifting forks, nice storage for weights if you're taking them out to customers to calibrate their balances. Here you see an example of a secondary draft shield. Manual handling of 50 and 20 kilogram weights can be a little bit tricky, so you could consider a hoist with a slow enough speed to raise and lower the weight successfully. If you haven't got connection to a PC, maybe a data printer can print out the results. And for the highest value of weights, you can get what we call a centering pan to help reduce the corner load errors. So that brings me to the end. So thank you. I hope everything followed nicely through the presentation. And if you have any questions, I'll try to answer them. Or if you submit the questions afterwards, I can look to send the answers back.
Thank you very much, sir, for your kind and brief presentation. Santosh ji, kindly make all the participants panelists so that we
Okay,
can
sir.
take the
Okay.
photographs for our
Yes.
Twitter handle. And sir, my request is if you kindly switch on your video, we can also take your some few of the
Okay.
pictures
I will.
for uploading on our official website.
Yes.
Sir, there are few things which I would like to ask you. See, for verification or the calibration of these even class weights, whether we can continue with the even class or we should go for E naught class, E0. What do you
Yeah.
suggest?
E naught, or sometimes they're called RS, are really needed if you're looking to calibrate class E1. We did have one customer who bought a mass comparator from us with the integrated software, and he was trying to calibrate E1 weights with E1 references. And every time he failed on the uncertainty contribution in the weighing process, simply because if you use the same quality reference and test weights, the contribution from the testing weight and the reference weight, it's just too high. You must always have one class higher. And I know it's difficult with E1 to find, maybe NPL would be the only people to give you an E0 type weight calibration.
But sir, how? Because as far as OML is concerned, it does not speak about E naught class weights.
No, they
So
don't.
what?
Yeah, yeah. They're theoretical weights. So basically, it's an E1 weight that is being calibrated with a much lower uncertainty. So,
Okay,
so
okay,
the uncertainty on that weight will be low enough in the
okay,
process not to over contribute.
okay. Okay, sir. Secondly, suppose we are considering a robotic mass comparator which has a range from 1 milligram to 1 kg, maybe in dual ranges, up to 5 gram or 10 gram. It may be in micro, ultra micro, and then above that it may be in the micrograms. So, will it be possible to have a single robotic mass comparator having from 1 milligram to 1 kg?
Uh, yes, in theory, and we ourselves have a mass comparator, not a robotic solution. It has two comparators built in, one robot and two comparators. So you have a comparator that is measuring from 0 to 10 grams, with a 0.1 microgram readability, and then a 1 kilogram with a 1 microgram readability. And with this, you can calibrate it E0, E1, all weights from a milligram to a kilogram.
Okay, thank you. One thing more, what you people are thinking about the realization of SI unit of mass, whether you are considering to have the silicon sphere or you are developing cable balance, what Mettler is, Sutter is thinking about it.
Yeah, the NMIs globally, as you probably already know, is that we have two experiments that were running side by side. The Avogadro experiment, which was producing a silicon sphere that was as close to 1 kilogram as possible. They could measure the volume accurately, and because of the lattice uh, construction of the purest silicon 28, they could estimate the number of atoms and therefore its mass. Alongside was the experiment with the what originally was called the Watt balance, but after Professor Brian Kibble, it was renamed as the Kibble balance. And this has been the method for now producing the actual theoretical and calculated 1 kilogram. And today there is, I think it's 4, maybe 5 NMIs that are all measuring using their own Kibble balance, which has been built to work at the range of 1 kilogram. And they have what's called the consensus kilogram. So it's an average of each of the 5 laboratories, 4 or 5 laboratories, estimation of the kilogram. And this is the method that's now used and was adopted, I think, 4 years ago as the new definition for the kilogram.
Yes. So, but whether you are also thinking to make it commercialized or something, you are also working on it?
Well, we do have, NPL has the older model, and we now have a newer vacuum mass comparator, which can compare up to 8 silicon spheres or silicon spheres and density references for air buoyancy, or just artifacts, or your 1 kilogram national standard. So vacuum comparators are available from Sartorius. We have a collaborative experiment with the University of Ilmenau to produce a small Kibble balance in the range of 200 grams. It's not commercially available. Price-wise, it would be very expensive, but the concept is to use it as a mass comparator because you don't need the reference weights. You have the Kibble balance concept means you can calibrate E-weights without any references. Not commercially available as of yet. Cost is very, very high to produce such an instrument. So we have to see for the future whether that happens.
Okay.
But yeah.
And when you are calibrating even class weights or the E2 class weights, whether you consider the magnetic susceptibility, hysteresis factors also in the uncertainty?
Yes, a very good question. There are susceptimeters available commercially from the main manufacturers, and they're consisting of a microbalance and a magnet, which is reversible, so you place your weight not on the weighing pan, but you place your weight on a resting position. Below there is the magnet, which is on the weighing pan of the comparator or the balance. You need to know your regional gravity. You measure then any attraction from the north pole of the magnet, any attraction or repulsion from the south pole, and there's usually a piece of software that will make the calculation to estimate if it can be magnetized or if it is already magnetized, what the level would be.
Okay.
So they're
Thank you,
called
sir.
susceptimeters. And
Thank you.
yes,
Okay. Thank you very much, sir. Sir, these are the few things. If any of the participant want to ask any question, because all of us are now panelists, they may also ask the questions if they wish. Sir, my request is again, if you kindly switch on your
I'm
video.
try I'm trying to find how to switch it on because I'm not used to this software.
Stop. Sir, it is video.
Yeah,
This tab of video must be there. Stop video and start video.
yeah. Video.
With the mute, unmute. The symbol which is there at the bottom.
Ah, the bottom. Okay, let me have a look at the bottom. I was looking at the top.
Mute, stop.
Ah, start video. Yes, I see it
Yeah,
now.
start video. Start video. Oh, I'm sorry. Yeah,
Yes,
now.
you have me now.
Yes, I can. I'm sorry. Actually, I could ask you in the beginning itself. That could be better. We can see your expressions and we could understand better.
Ah, okay. Yes.
Thank you.
Sorry
Thank you
about
very
that.
much, sir. Thank you. It's my pleasure. And certainly,
Yes,
we are always thankful to Sartorius. Whenever we are requesting, they are always helping us, not only in
yes,
India, in Germany, anywhere. We ask
yes,
them to help us. They are always, sir, Sartorius is one of the best company,
yes,
being German company. They are always helpful. With this, sir,
yes.
thank you very much. Thank you all. I think we can close this meeting with your
Yeah.
permission. Thank you, sir. Thank you.
Thank you.
Thank you
Sir,
very much. Thank you.
See my colleague there, Ashok. Good morning, Ashok. Afternoon for you all, as it is.
Yeah,
Thank you
good
very much,
afternoon,
sir,
Tony.
for co-hosting with me. It was a pleasure to be able to present to you. And any further questions, you can direct to Ashok or directly to me. And
Thank you.
I'll
Thank
do
you.
my
Yeah,
best
Thank
to
yeah.
you.
answer.
I
Thank you.
think, sir, one question is there. Somebody is asking.
Okay. What was the
No, I
question?
don't. No.
No.
So if there will be questions, we will send him by
Yes.
email and we can get
Yes.
the reply and share it. Thank you. Sir,
Perfect.
we will, with your permission, we are sharing your presentation and today's
Yes.
video in our YouTube channel as well as on the website.
Okay. You're very welcome. Thank you very much.
Thank you. Thank you
Thank
very much,
Good
sir.
day.
Thank you.
Good